Okay, hello everyone, and welcome to the third exercise session. Our topic for today will be magnetic mechanics coupling. And for that behalf, I have provided you with a demonstration example that I've uploaded on Teach Center just a few minutes ago. So if you download the zip folder, unzip it, you can follow the YouTube video step by step. So the files in the zip folder are these three. So there is an XML file, simulation file, the journal file, and the material file. So first of all, let's have a look at the geometry we are considering. Let's have a look at the geometry in Trellis. Okay, open the journal file and execute the first few lines so that we see the geometry setup. Looking like this. So we have three different regions. The green region is again the coil, the toroidal coil. So it's an axisymmetric setup again. So the y-axis here is the rotation axis. The light green or neon green region here is the coil, the toroidal coil, with an impressed current density in phi direction. And let's wait for it to load. Takes forever. Okay, and these three regions here, come on, 1, 2, and 3. This is the plate. This is an iron plate. So actually it's a disc. If you think about the axisymmetric setup, it's a very thin cylindric disc, which is fixed at the outer boundary here. So this line here has 0 mechanical displacements in x, y, and z direction. So it's clamped at the outer boundary, this disc. And when we excite this coil with an alternating current, it results in, of course, an alternating magnetic field. And if you have time derivatives, of course, you have induction effects, and you have, in conductive materials, you have eddy currents. And in this case, eddy currents will occur in electrically conducting materials. And the only electrically conducting material in this setup is the plate. The coil itself, we don't assign any electric conductivity to the coil, so we model this coil as an air coil, and by doing that we prevent eddy currents in the coil. This models a so-called stranded coil, which means, in practice, which would mean that the coil is made up of very thin litzes, so a litz wire. And the reason for the litz wire, of course, to prevent eddy currents. So by assigning 0 electric conductivity to this coil region, we prevent eddy currents, but not in this plate material, which consists of maybe iron or aluminum, some electrically conducting material. Okay, now let's continue with assigning the blocks. So the regions, including the boundaries. This should not take too long. Okay, so let's have a look at the. Okay, so we have 3 blocks here, so 3 regions, which is the coil region, of course, the plate, as I've shown you, and surrounded by the air domain. And as always, for partial differential equations, we need boundary conditions. And where do we assign boundary conditions? Of course, at the boundaries. So for the magnetic simulation, we need to assign a flux parallel boundary condition at the outer boundary of this domain and at the plate, at the inner vertical line of the plate, so that we have a closed surface where we apply a flux parallel boundary condition. Then, so this was the magnetics boundary condition, and the mechanical problem. For the mechanical problem, we only consider the plate region, since we don't want to compute the mechanical deformation of the air, which would be kind of nonsense, and we also don't want to compute any deformations of the coil. So for the plate, the mechanical boundary condition, we fix this plate, as I've said, at the outer boundary. So we need a region, a node set at the outer boundary, at the outer boundary of the disk, that we can assign or use in the XML file. Okay, so now let's continue with the mesh. Here we use a map algorithm, which means we're meshing with structured rectangles. Let's apply the meshing. Okay, here you see the final mesh, which is, as expected, a structured rectangular mesh. And what is obvious, that in the plate region, the mesh is very, very fine in thickness direction of this plate. And the reason for that are eddy currents, the skin effect. So as you've heard, I hope you've heard in the lecture about the skin effect approximation, so the depth skin, the approximation of the skin depth. And we need to resolve this skin depth approximation with about, I don't know, 5 or 6 elements. And so by increasing the frequency of the excitation current in the coil, the skin depth gets smaller, since the frequency is in the denominator of the skin depth approximation. So if we compare the skin effect, the eddy currents for an excitation with 10 Hertz compared to a simulation with 10 kilohertz, we would notice severe differences in the eddy currents of the plate. Maybe we can also, I will show this in the simulation as well. And the only thing left to do is to export the CDB file. So the mesh file that we're using in OpenCFS. Okay, that's done. We can close Trellis. We don't want to save that, no. And let's start Eclipse. Okay, and as always, I have no idea why the shared folder is not saved here, so we need to load it in again. We click on File, New, Project, Examples. Okay. And we can delete all the unnecessary folders and only keep the share folder. Okay, then we can navigate to the demo example. In my case, it's this folder, and open the coil transient XML file. Okay, now that it's finally open, let's have a look at the simulation definition. And as always, we first read the mesh file, which is the previously exported geometry.cdp. We load the material file, mat.xml. We define that the domain type is an axisymmetric setup. And here we can also define the variables we use later on. And of course the regions we're using, and here we are assigning the material. And the air domain has the material air. The coil is a proforma copper material, but if we have a look at the material.xml, we will see that the copper coil material has 0 electric conductivity. If it finally opens. Okay, so the air has 0 electric conductivity. The copper coil has 0 electric conductivity as well, so it's an air coil. The only electrically conducting material is this plate region. Then we can define points and elements at certain locations and assign them a certain name. And we can use this name later on to export certain results at these specific locations. Okay. We skip this FE polynomial list, since here you can choose if you're using Lagrange or Legendre polynomial, which kind of integration order, but this is an advanced topic, so we skip that. It works by default, and we are conducting a transient analysis since we want to investigate the mechanics, magnetomechanics coupling with the Lorentz force. And as you know, the Lorentz force density is JXB, and in order to have a J, so a current in the plate region, we need eddy currents, and we get these eddy currents with induction, so we need a time-dependent problem, eddy current problem. So we're conducting a transient simulation with 60 time steps, for example, and a delta t that is suitable for the frequency. So if we discretize the period length with, I don't know, 20 time steps, it's totally sufficient. Okay, then we're defining that the magnetic PD shall be solved in all 3 regions, and we define the boundary conditions, the flux parallel boundary conditions. And so here we define the boundary condition flux parallel at the outer air domain, at the inner plate domain, which was at the symmetry line, and this is wrong. So we don't assign a flux parallel boundary condition at the S plate outer, at the outer boundary of the disk, since this is automatically enforced through the transmission conditions. Okay, then we're using a coil, or we're defining the coil. It's a current-driven coil with a time-dependent value. So the signal we're imprinting on the coil has the amplitude of current times the number of windings times the sine or a cosine or whatever signal, time-dependent signal you want to apply, times 2pft. This is so omega t. Then we're assigning the region of the coil, and also important, the direction the current has to face. So in this case, we have an axisymmetric setup, and the only physically correct direction is the phi direction in the coil. And we store the magnetic flux density at all regions. So this will result, so defining the all regions tag will write out the results in H5 format so that we can open it in ParaView. And we also want to export the magnetic flux density at the element PLM. So this PLM has the location that we've previously assigned here. So at 0 radius and set coordinate 0.005. Take care in CFS. Our set in an axisymmetric setup correspond to x and y coordinates in cylindric cylindric coordinates. So in trellis, which is using the Cartesian coordinates, r is the x coordinate and y is the z coordinate. Okay, so we are exporting the flux density at this location, and this results in a text file. So the flux density at this point is exported into a text file. I will show you in a few moments. We also export the magnetic Lorentz force density, so the JXB. And if we integrate the Lorentz force density over the whole region, we get the total, so the total force, not a density, it's the real force acting on the plate. And of course we export the eddy current density. This does not really make sense since we only get the current we're prescribing. So we can delete that. And yeah, I want to comment the mechanical PD out for the first simulation and also the coupling list that I will discuss in a few moments. So now we're only solving the pure magnetic problem, the eddy current problem, the time dependent problem. So if we open a new tab and type in CFS coil transient, we're solving 60 time steps. Okay, and let's have a look at the result in ParaView first. So at the field, and load the volume regions, so the surfaces actually. Okay, and let's have a look at the magnetic flux density. Okay, magnetic flux density, this is the magnitude plot. We don't really get much information out of that, so we want to look at the glyphs at the vector field. And we click here on glyphs, assign that the vectors shall be oriented according to the magnetic flux density vector. Click apply. Maybe we have to rescale it. Yeah, we need to downscale the size, and here we can see the B field. So in order to have the same color in all regions, we assign solid color to these glyphs. And what do we observe? We have, of course, the flux parallel boundary condition at the boundary. which is correct, and the B field behaves as expected. And yet, since this is a time-dependent problem, we can click in this selection field here and scroll through the different time steps. So we should see an alternating magnetic field. We can also animate this by clicking on the play button. Hopefully the VM is strong enough to visualize it. Now it's decreasing and switching the direction, as you've seen. Now it points to the other direction. And this switching, respectively the time derivative, induces eddy currents in the conducting regions. And the conducting region here is the plate. So if we visualize the magnetic eddy current density, which is 0 in the air and the coil domain, so we uncheck the air and coil region, we only stay in the plate region. Maybe we go back to time step 0. Okay, and what you see here, let's zoom in a little bit, is that the red, don't get confused with the color, red here is minus 4.2 E3 and blue is much higher, 4 orders of magnitude higher. So we have much higher eddy current density at the bottom part of the plate, which is obvious since this is the side that is oriented towards the coil. So it has the higher eddy current density. Okay, and let's have a look at the Lorentz force density. So this is the magnitude plot of the Lorentz force density, and as expected, the highest force is acting here in the region where we have the highest currents or eddy currents. And we can also visualize the force acting on this plate by again clicking on the glyphs and the orientation array according to the magnetic Lorentz force density. So this here, we scale it. These here are the force vectors at every element, and you can also visualize them. So here we have a net force acting in positive y direction. Now it's switching. So we expect an up and down movement like a membrane of this plate, since we have fixed it here on the outer boundary. Okay, so this was the magnetic field and the Lorentz force density. And this Lorentz force density is the input for the mechanics PDE. So first of all, we solve for the magnetic PDE, export the Lorentz force density, read in the Lorentz force density in the mechanical PDE, and solve the mechanical problem. And this is done by assigning by inserting a second PDE in the PDE list. So right after the magnetic problem, we define the mechanic problem. And the mechanic problem, again, it's an axisymmetric setup. And we're only solving the mechanical problem in the plate region. As I've said in the beginning, we don't want to solve it in the air or in the coil domain. And we fix the outer boundary of the disk. So we set the R and Z components to 0 by applying this fixed boundary condition. And now we need the excitation of the mechanical problem, which is done by assigning a right-hand side. And the right-hand side in the mechanical problem is a force density. And force density for the force density, we read in the magnetic Lorentz force density from the magnetic PDE that we've previously defined here. So by executing this XML file, we sequentially solve the PDEs that we've defined in the PDE list. So first the magnetic PDE, we export the Lorentz force density, read it in as an input for the mechanics PDE, and solve the mechanics PDE. If we're interested in higher deformations, we then would need to solve the magnetic problem on the deformed geometry again, which is an iterative process. So this coupling is called an iterative coupling, and it is controlled via these lines here, where we define the iterative coupling. So we're looping between the mechanics until we reach a certain convergence criterion. And in this case, the criterion is the mechanical displacement and the magnetic Lorentz force density, which should have a relative residual of 1 to the power of -6 between two successive steps. Okay, now let's execute this. It should take a little bit longer than the pure magnetics problem, since we're additionally are solving the mechanical problem. Okay, now let's open ParaView again. And load the surface regions. Okay, then we have the same results as we had before, so the magnetic eddy current density, flux density, and the Lorentz force density. And now, since it is a coupled problem, we also have the mechanical displacement available here as a result. And as I've explained to you last time, the difference between the depicted hexahedral here and this dot just means that this dot is a nodal result, and the eddy current density, flux density, and so on are derived results from the primal solution quantity. And in the magnetics problem, the primal unknown is the magnetic vector potential. And so the flux density is then a derived result based on the vector potential, since B is curl A. So now let's have a look at the mechanical displacement. And we see we don't have results for the air and the coil region, since we're not interested in these. So this is the disk with the rotation axis here, and yeah, this is the magnitude of the mechanical displacement vector plotted in colors. We can simulate or animate the deformation of this disk. So let me just center it. Okay, by clicking here on the button Warp by Vector, and it automatically selects the mechanical displacement as the warping quantity. Click Apply, and you should see well, you should see, let's see, blow up the scaling factor. Okay, now you start seeing it. If I then step through the different time steps, you see the actual deformation. So it's not the actual deformation, it's exaggerated since I've applied the scaling factor, but you get the idea how the disk is moving due to the alternating impressed current density. So let's animate this. Looks quite cool. So it's a membrane, actually a membrane, which can, for example, be used in a loudspeaker. Yeah. And since we're using an axisymmetric setup, the rotation axis here, the inner vertical line here, is always oriented exactly in y direction. So it will not rotate around the z-axis and will not move in x-axis, since this would violate the axisymmetrical kind of boundary condition or modeling strategy. Okay, so this is the mechanical deformation. Now let's observe the text quantities. So we have not only defined the field quantities as a store result in the magnetic PD, but also we expect the magnetic flux density at one location. Okay, so this result here, and also the mechanical displacement at the defined node, and yeah, the Lorentz force, then so the Lorentz force, the total integrated Lorentz force, should also be available as a text result. And these text results are stored in a history folder. So after you execute the simulation, after you run the simulation, there is a folder history in your simulation directory. So enter this history folder and you see different files. And it is quite self-explanatory, since the name of the result is given here. And if you investigate, for example, the flux density at a certain element location, you get a vector, of course. In the axisymmetric setup, the vector consists of R and Z components. So the second and third column are the components of the B field, and the first column is the time. So you have the time signal of the B field. What else do we have? We have the Lorentz force, total Lorentz force at the air, coil and plate region. So we expect 0 Lorentz force at the air region, since there are no eddy currents. Yeah, okay, that's correct. And we expect non-zero Lorentz forces in the plate region. Okay, also correct. Non-zero Lorentz forces in the plate region. And again, you have the time signal, of the Lorentz force. So this is a total Lorentz force in the whole plate region. Okay, and the last one is the mechanical displacement at the defined node. And again, you have the time signal, or the time evolution of the mechanical displacement. And as you know, the mechanical displacement is a vector quantity. So again, you have the R and Z component of the mechanical displacement. Okay, that is it that I wanted to show you in this demonstration example. So I will stop the recording now.